Imagine looking at a spiral galaxy from far away. It appears calm, beautiful even, a bright center surrounded by enormous curling arms filled with stars, gas, and dust. Now imagine measuring the speed of those stars. That is where the comfortable picture starts to crack. Vera Rubin was born in Philadelphia in 1928 and became fascinated with astronomy while she was still young. She eventually studied astronomy at Vassar College, then continued her education at Cornell and Georgetown after encountering barriers that were common for women in science at the time. One especially important obstacle involved Princeton. Its graduate astronomy program did not accept women during the period when Rubin sought admission. Rather than treating that rejection as the end of the road, she continued her studies elsewhere. Her career eventually brought her to the Carnegie Institution in Washington, D.C., where she worked with instrument maker and astronomer Kent Ford. Their collaboration became especially important because Ford had developed a sensitive spectrograph that allowed them to measure the motion of stars in distant galaxies. The question was simple enough to state: how fast are those stars actually moving? You might assume the answer should depend strongly on distance from the galaxy's center. In our solar system, it does. Mercury travels around the Sun much faster than Neptune because the planets are moving under the Sun's gravitational influence at very different distances. Galaxies, however, are not miniature solar systems. They contain enormous numbers of stars, gas clouds, and other materials spread across huge regions. If you calculate how much visible matter a galaxy contains, you can estimate how its gravity should affect the motion of stars at different distances. Rubin and Ford found something unexpected. The outer stars were moving far faster than the visible matter seemed capable of explaining. And this wasn't based on one peculiar galaxy. Their observations eventually covered more than 60 spiral galaxies, revealing a recurring pattern. The outer regions were rotating at speeds that stayed surprisingly high instead of declining in the way a simple visible matter model would suggest. For you, the important point is this: Rubin wasn't staring through a telescope and seeing dark matter. She was seeing its gravitational consequences. That distinction matters enormously. The unseen material was inferred because something visible was behaving strangely. Stars were following motions that suggested additional mass had to be influencing them. And once astronomers accepted that possibility, the mystery became much larger than one unusual galaxy. Here's the central idea. A galaxy can contain far more mass than the part we can directly see. The stars provide light, gas can emit radiation, dust can block or scatter it. Telescopes can collect signals from these ordinary components across enormous distances. Dark matter is different. Scientists infer its presence primarily through gravity. It doesn't appear to shine like a star, and its nature remains unknown. Rubin's work became powerful because the same strange rotation pattern appeared repeatedly. The speeds measured far from galactic centers were too high to be comfortably explained by the visible material alone. Think of a huge carousel. Suppose you can see only the riders sitting near the middle. But somehow the people standing around the outside are moving almost as quickly as everyone else. You would immediately suspect that your picture of the carousel was incomplete. That's roughly the conceptual problem astronomers faced. The visible galaxy wasn't necessarily the whole galaxy. A large amount of unseen mass could create an additional gravitational field, allowing stars far from the center to orbit at the speeds observed. This is one reason dark matter became such an important concept in modern cosmology. It isn't merely an explanation for one measurement. Dark matter is also important in models describing how cosmic structure formed and evolved. According to the current standard picture, ordinary matter makes up roughly 5% of the universe's total energy-matter budget, dark matter about 27%, and dark energy roughly 68%. These percentages describe the cosmological model, not three substances that have all been directly collected and identified in the laboratory. That distinction is easy to lose in dramatic headlines. Scientists know ordinary matter exists because we can observe and measure it directly. Dark matter is supported by multiple gravitational observations, while its underlying particle or physical nature remains unknown. Dark energy is a separate mystery. It is associated with the accelerated expansion of the universe. Scientists can measure the expansion history and model its effects, but the physical explanation for dark energy remains unsettled. So when someone says, "We understand only 5% of the universe," that doesn't mean astronomers know absolutely nothing about the other 95%. Quite the opposite. We know a surprising amount about what dark matter and dark energy do. What we don't know is what they fundamentally are. And that is the doorway Vera Rubin helped open. Her observations shifted the question from "why are these galaxies rotating strangely?" toward something much more ambitious. What invisible mass is shaping the universe? There was another clue hiding in the data, though. If invisible matter surrounds galaxies, then gravity should leave fingerprints on much more than stellar rotation. Those fingerprints are exactly what the next generation of surveys is designed to search for. The scale of the problem is difficult to picture because our everyday intuition was built for things we can see. You can see a tree. You can touch a wall. You can watch a planet cross the night sky. Now consider something whose existence is inferred because it changes the motion of visible objects. While the thing itself remains hidden from ordinary telescopes, try this mental experiment. Imagine walking through a city during a blackout. Every building is dark, every street lamp is off, and visibility is terrible. Yet you have a strange pair of sensors that can measure how the ground vibrates whenever something heavy moves. You can't see the trucks, but you can map their paths. You can estimate their masses. You can even work out where traffic must be moving. That is closer to the logic behind much of dark matter astronomy than simply saying, scientists found invisible stuff. The universe provides visible tracers, stars orbit, galaxies cluster, light bends around massive structures. The expansion of the universe changes over time. Each effect contains information about things we cannot observe directly. For you as the viewer, there is another scale problem. A galaxy isn't a collection of stars sitting in a neat disk. It is an enormous gravitational system extending far beyond the bright region you see in photographs. If dark matter forms a surrounding halo, then the glowing portion of a galaxy is only one component inside a much larger gravitational structure. That makes the night sky deceptive. The most obvious objects are not necessarily the dominant ones, and the numbers get enormous quickly. Rubin Observatory is designed to build a massive census of the southern sky, with estimates reaching roughly 17 billion resolved stars and 20 billion galaxies over its survey lifetime. You don't need to imagine Rubin taking a single photograph containing every one of those objects. Instead, think of it as building an enormous time-dependent database. The telescope repeatedly observes regions of the sky. Each visit adds information. Stars change brightness, asteroids move, supernovae appear. Galaxies reveal subtle patterns in their shapes. And repeated observations matter because some of the most valuable information isn't contained in one image. It is hidden in the difference between images. That turns astronomy into something surprisingly similar to watching a city through thousands of security cameras, except the cameras are looking across billions of light years, and the events can unfold over minutes, years, or even longer. Rubin's job isn't simply to take prettier pictures. It is to measure change at extraordinary scale. That requires a machine capable of collecting enormous amounts of information without drowning researchers in it. And that is where Rubin's most famous piece of hardware enters the story. At the heart of Rubin Observatory is the LSST camera, a 3.2 gigapixel instrument described by the observatory as the world's largest digital camera. Its field of view covers about 6 square degrees, and it uses 6 optical filters to record different colors of light. The camera is enormous by astronomical standards. It was built to repeatedly photograph huge sections of the southern sky, allowing scientists to compare observations over time. That repetition is crucial. Suppose Rubin observes a patch of sky tonight. Tomorrow, the same region can be observed again. Software compares the new image with earlier data and identifies meaningful changes. An asteroid shifted position, a star brightened, a distant explosion appeared. A galaxy's apparent shape contains a subtle gravitational distortion. Each change can become an alert. Rubin's alert system is expected to generate around 7 million alerts per night, with a target latency of roughly 60 seconds between observation and alert distribution. Automated alert brokers then help sort and classify that flood of information. 7 million alerts isn't 7 million discoveries. That's an important distinction. Most alerts will represent ordinary changes or objects already familiar to researchers. The challenge is finding the rare events hidden inside that torrent. It's like receiving millions of weather readings every night and needing to identify the one measurement that hints at a developing storm. Now connect this system to dark matter. Rubin can study weak gravitational lensing, where the gravity of foreground structures subtly distorts the apparent shapes of more distant galaxies. Those tiny distortions can help astronomers reconstruct how mass is distributed across large regions of the universe. The telescope can also study stellar streams. These are long structures made from stars that were once part of smaller systems and have been stretched by gravitational interactions. Their shapes and motions can preserve information about the gravitational environment around the Milky Way. If dark matter is distributed unevenly, those structures can carry clues about it. Rubin is therefore attacking the mystery from several directions at once. It can study galaxies, it can study the large-scale structure of the universe. It can examine changes in distant objects, it can map gravitational distortions, and it can repeatedly return to the same regions, creating a time-lapse record instead of a single snapshot. The 10-year LSST began in June 2026 and is designed to observe the southern sky repeatedly, using 6 filters and a wide field strategy. That means Rubin isn't waiting for the universe to produce one magical signal. It is gathering an enormous statistical picture. And that changes the kind of question scientists can ask. Instead of asking whether one galaxy behaves strangely, they can ask whether billions of galaxies follow patterns predicted by competing cosmological models. That is where the story moves from Vera Rubin's original discovery to the much bigger test now underway. The boldest possibility isn't that Rubin Observatory will suddenly photograph a dark matter particle. It won't. The telescope is primarily an optical survey instrument, so its strength is measuring the gravitational and visible consequences of cosmic structures. The exciting possibility is that those measurements could reveal whether our current description of the universe is missing something important. Dark matter is one side of the problem. Dark energy is the other. And the two should not be confused. Dark matter helps explain how cosmic structures gain and maintain their gravitational organization. Dark energy is used to describe the component associated with the universe's accelerated expansion. Rubin was specifically designed to investigate both. Now consider what happens if observations consistently disagree with a leading cosmological model. That doesn't automatically mean the model is destroyed. Science is rarely that dramatic. Researchers would first check calibration, systematic errors, selection effects, assumptions about galaxy formation, and alternative explanations. Independent observations would matter enormously. But if multiple lines of evidence continued pointing in the same direction, physicists could face a deeper problem. Maybe dark energy isn't behaving exactly as the simplest model predicts. Maybe our understanding of how structures formed needs adjustment. Maybe dark matter has properties more complicated than the leading candidates suggest. Or perhaps the current framework survives every test. That last possibility is scientifically valuable too. A powerful experiment doesn't need to overthrow a theory to succeed. Sometimes its greatest achievement is showing exactly where a theory works and where it doesn't. And Rubin's timing is remarkable. The observatory has now begun the LSST, while NASA's Nancy Grace Roman Space Telescope is scheduled for launch on August 30th, 2026. Roman is designed to investigate dark energy and dark matter using a different observational approach, and its field of view will be at least 100 times larger than Hubble's. Ground-based Rubin and space-based Roman are not simply copies of each other. Their instruments, wavelengths, observing strategies, and scientific strengths differ. That is exactly what makes the combination interesting. Imagine 2 investigators examining the same mystery using different tools. If both arrive at compatible conclusions, confidence grows. If they disagree, the disagreement itself becomes useful. There is also a deeper twist. Rubin's survey is not narrowly about finding one answer to one question. Its data will cover asteroids, variable stars, supernovae, galaxies, the Milky Way, dark matter, dark energy, and phenomena scientists cannot predict in advance. So the telescope could uncover something that isn't even on today's list of priorities. That possibility is built into the mission, and yet there is a serious reason not to turn every new signal into a headline. Astronomy has learned that unusual does not automatically mean revolutionary. The next section explains why. Dark matter is strongly supported by a broad range of observations, but that does not mean scientists have identified the particle responsible. That distinction is essential. For decades, physicists have searched for candidate particles, including hypothetical weakly interacting massive particles, often called WIMPs. Numerous experiments have looked for interactions between dark matter candidates and ordinary matter. So far, no experiment has produced universally accepted direct evidence identifying a dark matter particle. That means Rubin cannot simply point its camera at the sky and announce, "There it is." Its contribution is different. Rubin can improve measurements of how matter is distributed and how structures evolve. It can test predictions, it can expose tensions between observations and models. Those are powerful capabilities, but they don't eliminate uncertainty. There are also alternative ideas in physics. Some researchers have explored modifications to gravity or other explanations for galaxy dynamics. These proposals face their own observational challenges, and none has replaced the broader dark matter framework across all major lines of evidence. This is where scientific skepticism becomes useful rather than frustrating. Suppose Rubin finds a strange pattern in galaxy shapes. The first question won't be, have we discovered dark matter? It will be, could anything else produce this pattern? Could the telescope's calibration be responsible? Could the galaxies have properties we misunderstood? Could our simulations be incomplete? Could a statistical effect be masquerading as a physical signal? Those questions sound less exciting than a dramatic announcement. But they are what make a result trustworthy. You can think of scientific evidence as a lock with many tumblers. One observation may move one tumbler. Several independent observations moving together are much harder to dismiss. That is particularly important for cosmology because the universe is not a controlled laboratory experiment. We cannot reset the cosmos and run it again with one variable changed. Instead, researchers compare enormous populations of objects and look for patterns that remain stable across different methods. Rubin's value comes partly from this scale. It can provide a huge observational sample against which theories can be tested, and its data stream has already demonstrated the observatory's ability to detect enormous numbers of changing or moving objects. Rubin issued its first scientific alerts in February 2026, initially producing about 800,000 alerts in one night before the system scales toward its expected millions per night rate. That early result is important. But it isn't evidence that dark matter has been directly detected. It is evidence that the machinery for real-time astronomical discovery is operating. The distinction may sound technical. It isn't. It is the difference between having a powerful new microscope and already knowing what the thing under the lens is. Rubin has delivered the microscope. Now scientists get to see what repeatedly looking through it reveals. Strip away the speculation, and the achievement is already extraordinary. Rubin Observatory has begun its 10-year legacy survey of space and time. The survey started in late June 2026 from Cerro Pachón in Chile and is designed to create a massive, repeated record of the southern sky. This is not a proposal anymore. It is operating. The observatory is taking hundreds of images during nightly observing and collecting roughly 10 terabytes of data per night. While its alert system can generate as many as 7 million notifications about changes in the sky. The numbers are almost difficult to visualize. Over the full survey, Rubin's estimates include about 20 billion galaxies and 17 billion resolved stars. It is also expected to identify millions of objects in our own solar system. That alone would be a monumental astronomical catalog, but the deeper achievement is repetition. Rubin isn't simply building a giant photograph. It is constructing a record of how the sky changes. That matters because the universe is dynamic. Stars explode, some stars pulse, asteroids cross the sky, black holes can change their brightness as matter falls toward them. Galaxies contain transient events that appear and fade, and gravitational structures leave patterns in the distribution and distortion of light. A survey that watches these changes systematically can connect events that previously appeared unrelated. That creates opportunities for follow-up observations by other telescopes. A Rubin alert can tell researchers that something changed and where it happened. Other observatories can then examine that target with instruments sensitive to different wavelengths or physical processes. In other words, Rubin is not meant to work alone. It becomes part of an astronomical network. The same philosophy applies to dark matter. Rubin can map its gravitational influence on enormous scales. Other experiments can search for particle interactions, space telescopes can probe different wavelengths, cosmologists can compare the results with simulations. No single instrument has to solve the entire puzzle. The real achievement is creating enough high-quality evidence that competing explanations can finally be tested against the same enormous observational record, and there is one especially valuable feature of this survey. The data won't only answer questions scientists already know to ask. When you repeatedly observe billions of objects, unexpected patterns are almost guaranteed to appear. Some will be mundane, some will be errors that teach researchers how to improve the system. And some may become entirely new scientific questions. That is the concrete payoff of Rubin, not a guaranteed revelation, a vastly larger window onto reality. And the telescope has only just started opening it. The timing of this mission gives the story a remarkable second chapter. Vera Rubin spent her career asking what could be inferred from the motion of visible matter. Now, an observatory carrying her name is measuring the universe on a scale she could never have accessed. The Rubin Observatory was named for her in 2019, and it is the first U.S. national observatory named after a woman. Its 8.4-meter Simone survey telescope sits on Cerro Pachón in Chile. The instrument is built around speed, sensitivity, and an unusually wide field of view. The LSST camera contains 3.2 billion pixels. A single exposure can cover roughly 9.6 square degrees of sky, and the survey will revisit the southern sky repeatedly for a decade. Now add another observatory. NASA's Nancy Grace Roman Space Telescope is scheduled for launch on August 30th, 2026. NASA says Roman will investigate dark energy and dark matter among its major science goals. That creates an unusually interesting period for cosmology. Rubin is already collecting wide-field optical observations from the ground. Roman will eventually provide wide-field infrared observations from space. The instruments won't answer identical questions in identical ways, and researchers will need to understand their differences carefully, but their datasets can complement one another. Then there are the particle experiments. Underground detectors continue searching for possible interactions between dark matter candidates and ordinary matter. Their strategy is fundamentally different from Rubin's gravitational mapping. That difference matters. If an underground detector eventually identifies a particle consistent with dark matter, astronomers could compare its properties with the large-scale behavior observed across galaxies and cosmic structures. If no particle appears despite increasingly sensitive searches, theorists may need to rethink which candidates deserve the most attention. Meanwhile, Rubin's data can test whether the gravitational effects attributed to dark matter follow the patterns expected from different models. The same goes for dark energy. Scientists want to know whether the accelerated expansion of the universe can be adequately described by a constant term in the equations, or whether observations point toward more complicated behavior. Rubin is designed to make precision measurements relevant to that question. Its science program includes mapping cosmic structure, measuring gravitational lensing, studying supernovae, and tracking how the universe's expansion evolves. And the first results will not arrive as one giant final answer. They will accumulate early discoveries, early data releases, improved calibrations, new catalogs, follow-up observations, then increasingly powerful statistical analyses. That process may feel slow compared with the speed of the alert system. The alerts can arrive within about a minute. Understanding what they mean can take years. That is normal. A notification tells scientists that something happened. Science begins when they determine why. There is also something beautifully appropriate about this mission. Rubin spent decades measuring galaxies and following the evidence wherever it led. The observatory named for her is built around exactly that principle. Watch, measure, compare, question the assumptions, then watch again. And somewhere in the enormous stream of measurements, researchers may find evidence that strengthens our current picture of dark matter, exposes a weakness in it, or points toward physics that today's textbooks don't yet contain. We cannot honestly promise which outcome will happen, but we can say something concrete. For the first time, humanity is about to have an extraordinary statistical record of how the visible universe changes across the southern sky. And that brings us back to the number that started this story. Remember the 95% figure? It sounds like a statement about ignorance, but it is more useful to think of it as a map of unanswered questions. Roughly 5% of the universe is ordinary matter. About 27% is attributed to dark matter. About 68% is attributed to dark energy. Those figures come from our leading cosmological model. They do not mean scientists have collected 95% of the universe in an invisible warehouse and simply forgotten to open the door. We know dark matter is associated with gravitational effects. We know dark energy is associated with accelerated cosmic expansion. What remains unknown is the deeper physical explanation, and Vera Rubin helped force that question into the center of modern astronomy. Her observations of galaxy rotation didn't reveal a glowing object hiding behind the stars. They revealed a mismatch between visible matter and gravitational behavior. The numbers refused to cooperate with the simplest picture. Rubin trusted the measurements. Decades later, the telescope carrying her name is doing something astonishingly appropriate, measuring the sky again and again, searching for patterns that ordinary snapshots would miss. The LSST began in June 2026. Millions of alerts are now part of its nightly routine. Billions of stars and galaxies are expected to become part of its enormous catalog. And the biggest question isn't whether Rubin Observatory will produce discoveries. It almost certainly will. The question is, which discovery will force us to redraw the map? Maybe dark matter will remain the best explanation, and its properties will become clearer. Maybe dark energy will reveal behavior more complicated than expected. Maybe an entirely different clue will emerge from an object nobody was specifically searching for. That is the strange gift of astronomy. We point a machine at the sky expecting answers to our questions, and sometimes the universe answers with a better question. Vera Rubin spent her life following those questions. Now, an observatory bearing her name is watching billions of cosmic objects change, move, brighten, fade, and bend the light around them. The universe has not stopped keeping secrets. We have simply become much better at noticing where the secrets are hiding, and the next clue may already be somewhere inside the data arriving tonight.